Okay, so I just wanted to share something, very different to what you might know, what I usually do, and in my normal role, which is to, I'm a sample analysis person. I work with lunar samples and all sorts of extraterrestrial samples. But something that has actually arisen out of that is my interest in the field of in situ resource utilization for the last 10 or so years. And more, I've got involved in that. I have started to think how all the work that we are doing for lunar ISRU, how could that be actually brought back to Earth or brought to Earth in the near term. So I'm confident that anything we do in this area over the next 40, 50 years will eventually have great applications here on Earth. But oftentimes there is a tension about how do you actually justify what you're doing on the moon for the benefit of all of us here on Earth. So that got me thinking. And I thought, okay, the only thing I know is, how to work with samples. So I'm a geologist by training, and I understand minerals, I understand rocks. And so about 10 years ago, my colleague Sangbu Lim and I started working on the concept of using microwaves for developing ISRU processes for lunar applications. And the reason was that we all heard over the last 2 days, especially yesterday, Matthias very eloquently shared with us how Moon is not just going to be a destination for humans to work and do experiments, etc. It's also going to be a gateway and an enabler for the wider solar system exploration. But that exploration has to be done in a sustainable manner, and that exploration has to be done in a responsible manner, which means that we are going to be compelled to minimize the wastage of any resource that we take with us, but also maximize the resource that are going to be available in situ. So where does our work fit in there? Well, when we get to the moon, the only thing that is going to be available to us in the first instance is going to be the lunar environment. And in that lunar environment, the main thing is the lunar regoliths, right? Again, the regolith is broken down from rocks. So as a geologist, if you understand what the lunar rocks are made up of, then you have a better understanding of what actually that regolith represents. And then regolith contains all sorts of records and history of the solar system and the galaxy and all that you would have heard many times before. So this is where the idea of applying microwave technique comes in, because we thought that when we get to the moon, we need a source of heat to process that lunar regolith, to convert it into some meaningful form. You don't have plentiful water, even if you have some water on the moon. So you can't use water in doing your construction activities. So you need something that actually can allow you to handle and process the regolith so that you can mold it into some meaningful structure. So building your habitat. And that's where the idea of using microwave heat source came to our mind, and there are some advantages for using microwaves as opposed to other heat sources. So that work was going on over the last few years. And then we also have colleagues here who are in the audience who have been doing a lot of experiment for extracting volatiles from lunar regolith, and that is what we are trying to demonstrate through one of the ESA missions called Prospect, using the Prospect package, where a payload will be sent to the moon, hopefully in one of the CLIPS mission now in the next few years. And that will be the first demonstration of how you can extract oxygen or water from the lunar regolith along with something else. So I thought, okay, we are doing so many things with the lunar regolith, but we are not trying, or we are not able to combine yet to maximize what you can get out of the lunar regolith. So that's where this idea arose. And then last year, I bumped into another bunch of colleagues from Finnish Geological Survey. And you heard from my colleague Alan Butcher yesterday about some of the work that we are doing with them. And they are experts in mining industry. So they are experts in actually dealing with the raw material, the circular economy, extraction of critical metals, etc. And to me, that's when the whole circle really became a circle. And I thought, okay, now we are in a place and with a group of people who actually understand the material, who understand what we need to do on the moon, and people who are actually today, they are involved in helping the terrestrial economy with regards to utilizing the raw material and making that economy as circular as possible. So that's where this work began. And so the first focus is on the lunar regolith, and this is a very well-known pie chart, and all you can see there is almost half of the lunar regolith contains oxygen. So you heard so much about water, you so much about oxygen. If you want to get oxygen on the moon, you need to extract that oxygen from the lunar regolith. It's not freely available. And if you are lucky to find the water ice, if you go to the polar region, well, maybe you can extract that oxygen much more easily from that. But if you don't go to the polar regions, or for some reason that ice is not accessible to you, you have no choice but to actually utilize the lunar regolith. So what else can you do after that? So that's where the PROSPA experiment can help us. But the remaining 50% or 60% of the regolith still contains meaningful material and some critical elements. Let's take an example. It could be nickel. It could be copper. We don't think about it, but that is something that is going to be critical here on Earth, because all of us want to drive electric cars. And they all require batteries, and all those batteries actually require nickel, cobalt, copper, and all sorts of elements that actually are widely present, but not present in ore quantities that you normally expect in ore deposit. So we had two-pronged approach. One was to develop application when we get to the moon, to do whatever we want to do, but at the same time, you utilize and translate that technology for terrestrial applications. Okay, so the first thing is, now everybody is aware that there is some form of water on the moon. It's either present as water ice, or it is present in its various forms as hydrogen, hydroxyl, or even molecular water, often trapped inside rocks, often trapped inside mineral structures. So on one hand, we can use the microwave technique or any other technique to extract that water or convert that into its component oxygen and hydrogen, could use as a fuel and for all sorts of other purposes. So we have a very deeper understanding of the water inside the moon, and it is growing every day. We are discovering new things, and then that is informing what we want to do and how we want to apply those techniques on the moon. And that is all underpinned by the laboratory research. I mean, I'm not ashamed to actually fly the flag for the laboratory scientists here who actually do very hard work with the minimal material that is available to them in terms of lunar material. And so a lot of our knowledge and understanding and the excitement about going to the moon and using it as an enabler of solar system is on the back of those. Okay, so I've got 2 minutes left. Those developments made by any of the early career scientists who are sitting here in this room, in fact. So we also know that we can find water on the surface of the moon, and later today you will hear from one of our PhD students, James Cole, who will tell you about his experiment using microwave, how he plans to extract water and oxygen from such water deposits. And again, colleagues are present here who are involved in that PROSPA and prospect package development for ESA, which hopefully will be flown on a NASA CLIPS mission and will be the first demonstrator for extracting oxygen. So this involved miniaturization of laboratory instruments that we use every day for the type of analysis that I described to you, but then fly this to the moon and do that experiment on the lunar surface. So there is a bit of payload development involved there, not a bit, quite a lot, should I say. And of course, in the process, you have some very, very many early career researchers getting the opportunity to be trained and skilled and become leaders by themselves. So that's very nice to see. And then once you have actually used the microwave to extract your water and volatiles, you are left with the material that you can use to build habitats. And then that's where we have colleagues like Sangu Lim and our recent PhD student, Vibha Levin Prabhu, who finished her PhD, and now she's working at ESRIC in Luxembourg. And so we have been looking at the possibility of using microwave for building habitats. And finally, we come back to Earth. And this is where what you see is some nice field pictures, and they look nice from a distance, but when you get closer, you see that what a barren desertic landscape it is. And I am in North Wales, and anybody who knows about the geography of the UK would not expect a dry and desert-like environment in North Wales. So this is on the island of Anglesey, and what it is mine waste. Thousands and thousands and thousands of tons of mine waste that has been produced in the process of extracting mainly copper. That area used to be the world's largest supplier of copper. So to take out copper, a lot of waste material has been produced. So what we are trying to do is we received some money from our funding agency, who is very keen to apply our scientific knowledge for applied purposes. And so we applied the microwave technique to mine waste remediation. And what we found was, take this example of this waste material from Anglesey. It had dispersed copper minerals called chalcopyrite. Now, this is very fine-grained distributed, and you wouldn't call it ore. It was rejected as a waste. What we found after doing the microwave processing, that you will see those circled areas, that suddenly nuggets of copper or the droplets of copper seem to have started to form. And that gave us an idea that probably using the microwave, we are beneficiating what was waste into some sort of meaningful ore deposit. So potentially, you can use this to extract your copper further. So what can you do with it afterwards, though? So, okay, this may be good for beneficiating copper. There may be other elements that people didn't know when they were mining. And as a geologist, you know that copper doesn't occur in isolation. It comes together with lots of other elements. So we came up with this flow chart. So on the left-hand side is all about the moon. On the right-hand side is all about the Earth. And this is how we think it could connect and make it a circular economy, where you have a mine with some material taken out, majority is waste. You process that waste in a traditional sense to extract something else that you didn't know it was there. And ultimately, whatever is left, you can make, well, this is my last slide, you can make 3D printed structures. And if you want, later on, you can actually come and examine these Lego-like bricks that we have printed using the mine waste. And so I have it with me. And on the left-hand side, what you see there is what we want to do on the moon. So we do the same process, but on the moon, we also want to extract oxygen before we extract the metals. And then after we have extracted that oxygen and metal, we want to use the remaining material for 3D printing. Okay, so that's how we see the two come together. This is only the beginning. It was a very small pilot project, and not my title, but recently, some of us here in this room contributed to this article published by the Chemistry World. And when Royal Society of Chemistry is also picking up about the race to build a base on the moon, that's good news, which means that more people outside our community are starting to recognize what we are doing. So thank you very much for your attention.